Swayam Prabha. Digital India. Educated India.
Welcome back to Real-Time Digital Signal Processing Lab. So, today we will discuss about DFT and FFT, whatever we have covered in theory. So, we will see first in MATLAB, then we will go to the DSP processor board and then see how we are going to run our code today. So, first we will consider the MATLAB thing. So, this example, as I was mentioning about the filters, so this is from the book Welch, Wright and then Morrow. So, you will be seeing that real time digital signal processing book published in 2005. There was an M file which shows that how the windows can be generated and then the filter responses for different kind of windows what we can see it. So, we will be applying one of the window for our DFT or FFT to remove the noise and then see that how they will be represented in the frequency domain. So, here the number of inputs what it is chosen is 128 and then alpha for Kaiser window is chosen as 3 and then number of FFT points chosen as 1024 into 8 and then the sampling frequency in this case chosen as 48,000. And then you will be representing that is line type control for the plot and then you will be setting the font size in the plot of MATLAB. So, first one we will be calculating Bartlett window with n points and then Hamming window, rectangular window and then the Kaiser window. So, we have to pass the alpha parameters which can be variable. So, you can select them as we have seen in filter design toolbox. So, you can generate this. Then you will be computing their frequency response. We call it as frequency Z basically. So, you will be calculating for the that is H3 what you have seen the thing W3 by sum of W3 what you will be putting it and then the sampling frequency what you will generate. And then the frequency response for H2 is shown that with this parameters and you will be outputting the figures actually. So, you will be plotting W3 that is subplot what we will be having it and then font size line width what it is shown and all the 4 figures what it will be plotted. So, with different colors and then later on you will be seeing that subplot what you are going to calculate that is P3 what it is chosen and then you will be finding these are the plot parameters one can go through. You will be getting help file in MATLAB and then you will be all these are the subplot. So, you will be seeing that you will be calculating Hamming window what it is going to be used and then its frequency after passing your data through that what you will be seeing it. So, we will run and then see how we are going to get the output. So, you can see the thing. You will be seeing the first the figure we will look at it. So, you will be seeing that this is a rectangular window and you will be seeing with the pink as a Kaiser window with alpha is equal to 3 what it has been selected and then Hamming window and this is the Bartlett window what you are seeing it is just like a triangular and then this is a rectangular and then the other two represent your smooth response. So, the second figure we will see what has happened. So, you will be seeing that in this you have passed through the rectangular window and then you are seeing the frequency response of after passing through the rectangular window, and then you will be seeing using the Hamming window. So, how the output is going to be represented. So, you will be seeing that this is our main lobe, this is a low pass filter basically, and then these are the side lobes. So, you will be seeing that rectangular window, you will be seeing it is has a main lobe is very narrow compared to your Hamming window, or any other window what you can take the thing, and you will be seeing the ripple somewhere in minus 14 dB or something like that what they have come down, and then finally it will be settling down to 21 dB or so. Whereas in the case of your Hamming window, this is a smooth response what you are having with your input signal. So, the main lobe is little bit increased, and then you will be seeing your side lobes have come down approximately what we can take it as minus 40 or 41 dB. So, this shows that how our filter helps in having the main lobe and then side lobe required for your application what you can select one of the windows, basically designing with windows. So, we will close this and then we will go to the DFT basically. So, here what we have is usually we ask the students to run DFT, FFT and then overlap add and save method. So, we will demonstrate today up to this thing. Okay. We will go with the DFT, FFT editor, because I can split the windows or editor can be in one of the thing. So, here we will maximize on the editor, so that you can see the codes what it has been written. So, initially we use the clear all. So, you should be calling back the theory. So, we did the circular convolution using DFT properties. So, we will be using in this case FFT to run our circular convolution. One of the way of doing it is I can put a breakpoint because the continuous code is running. So, I will be setting the breakpoint here, so that we will be seeing one after the other. So, first one is a circular convolution using FFT. As you can see that x has the value 1, 2, 3, 4 and then h is 1, 0, 1, 1. So, this example we manually worked it out. Now, we will see MATLAB how it is going to compute. So, we will be first what we are doing convolution, usually direct convolution as we have done it earlier. Now, using FFT how we are going to do the circular convolution, we look at it. So, first what we do is xk is our FFT of x and then hk is FFT of h what we will be taking it, and in the frequency domain we know that yk is going to be represented by a direct multiplication of hk into xk. So, that is our, as you can see yk is equal to xk into hk or hk into xk. Then what we will be doing is I can take the inverse FFT of the yk and compute and display circular convolution result. So, then accordingly we can do the linear convolution. So, how it is going to what are the values we are going to get it through a linear convolution is given by this equation. Now, what is it Ly linear y output what we will be getting it. So, the convolve is the command prompt in MATLAB. So, one can use it x comma h. So, it will be computing and display linear convolution results. So, we will run this code. Since I have put the breakpoint till here what it will be running. So, you can check the thing results, it will be displayed on the command window. So, I have to bring it down. So, you can see that as the convolution of circular convolution of 1, 2, 3, 4 and 1, 0, 1, 1, what we got the result was 6, 987 in the theory. So, you are seeing using the MATLAB, it was asked for you to verify with MATLAB whether you are going to get the same thing. And then the linear convolution, what you can see is it is 1247574 what we got it. So, that we will be seeing, that is direct convolution what it has been done. So, using the convolution whether we can do the linear convolution, that is what the example we worked it out. So, here you will be seeing that linear convolution by 0 padding in the MATLAB code what we had has been written. So, you will be 1 2 3 4 and you will be, we have added 1 to 4 zeros. So, this is zeros 1 to 4. So, it will be generating 1 2 3 4, 4 zeros followed by, and then the same way with HZ also 4 zeros what it has been added. Now, you will be doing the DFT of or FFT computation basically of our XZ and then HZ. Then we multiply in the frequency domain both of it. Okay. So, why we can take the IFFT of I of t and then we will be getting the results. So, just to show that I can put the breakpoint and then see that what our output is going to be. So, we will continue the running. So, we will see that the results are displayed here. So, you can see that what was the thing, the previous one we had 1247574 and then y is the what we have got the output with linear convolution and using FFT. So, you will be seeing that it is 1.0, 2.0 and then so on. The last one is minus 0 because we added one extra 0 in the thing because L plus M minus 1 as we know about it. So, it has to be 7. So, till there what you will have it, rest of them are zeros by doing the 0 padding. So, we will go back to the next this thing. So, I can maximize when I want to show you the results. So, we will reduce it and then go back. Now, what is it? So, we will calculate the amplitude spectrum of sine wave using FFT and then display it. So, here our this thing is number of samples, that is 256. We call it a sampling rate and then sine wave frequency what chosen is 50 basically hertz and number of points chosen is 120. So, this up to 128 points 0 to n minus 1. So, you will be calculating sine of 2 pi f by fs into n. So, that is how we will be getting our xn samples in input sample. Then we can calculate x of k, that is FFT of x of n comma n number of points, and then we will be plotting the absolute value of xk because we know that it is a complex conjugate what we will be getting it. Only the amplitude what I want to have the thing. So, we will be taking the absolute of x of k which gives us the plot the amplitude spectrum alone, and then this is going to give us the magnitude spectrum. So, for the axis is going to represent 1 to 64, show only up to points fs by 2. So, in this case what we have is 128 points which represents up to 2 pi or fs values. So, you will be labeling. So, what we will do is we will put a breakpoint again. So, I have to go down and then the select a breakpoint here. So, we will set enable the breakpoint here. So, you will be seeing where next the computation is going to happen, we will have the breakpoint. So, we can continue. This is to avoid multiple files, all the codes have been incorporated in one. So, you will be seeing that this is the for up to 64 samples what you have it. So, what we have is f is equal to 50. So, you will be seeing the magnitude whatever you are going to get the thing, and then the frequency index you will be seeing that it is at approximately 25. So, what you are having the frequency at k is equal to 25. So, can you compute and then look at it whether you are getting the frequency as 50 hertz. How it is going to be? So, you have to multiply it by 2, which you will be getting it as 50 hertz. Okay. So, now the next one is compute and display amplitude spectra at 2 sine waves. So, how we are going to do this? We hold on for a while. So, we will set the break point here also. So, you know that next break point is set. So, what we are going to do here? So, again our sampling frequency we have chosen as 256 sampling rate, and sine wave frequency is 50 hertz, and number of points what we have chosen is 128, and we will be calculating sine of the thing 50 hertz sine wave. So, we will be doing the FFT of this one and then calculate our this thing magnitude. So, this is what we did the thing. So, the next one is we will see that amplitude spectra 2 sine waves, what is going to happen. So, we will put up the next break point, it is already selected. So, it is the same thing. So, what you have is the first frequency is 50, F1 is 61, frequency of first sine wave, and then second sine wave what it has been chosen, and you will be calculating xn is sine 2 pi f by fs into n, and then x1 of n will be 2 star pi f1 by fs into n. So, generate 61 hertz, generate 50 hertz, then take xk is equal to FFT of the first input signal, and x1 k is of FFT of x1 comma n basically second sine wave, and then calculate their magnitude spectrum, first sine wave and the second sine wave magnitude spectrum, and then plot them with n values which is varying between 0 to 127. So, you will be only representing 1 to 64. So, when we run this, you will be seeing that how the two of them look like. So, you are seeing this is multiple, as you can see this is, you will be seeing at 50 hertz, and this should be at 31. So, you can see that approximately x is there 30, little bit movement will give select 31. So, that is what you are y magnitude is 40.7109 what you will be seeing it, and you will be seeing this if we put the thing x is 25 and then y is 64. So, you will be seeing that approximately you will be getting between 60 to 61 what you are seeing the thing, which is 61 hertz sine wave generated, whereas your peak is 25 for your 50 hertz signal, as because we are representing with 64 samples in the thing pi by 2 what we have done the thing. Okay. So, this is how your frequency spectrum and other things work. So, the next one is we are going to see that overlap of two spectral lines due to frequency separation is less than frequency resolution. So, how we have defined our frequency resolution, it is Fs by n what we have taken the thing. So, you have 256, here again n is 128, and F1 in this case sampling frequencies the frequency that has to be passed, first sine wave is 60, the next one is 61. So, compared to the previous one, so we have 1 hertz difference. So, we will see the resolution how it is going to be represented. Then we will be calculating x in and then x to n, generate 60 hertz and then 61 hertz as usual previous, then add them up and take the FFT of x in, that is mix these two sine waves and take the DFT computation, find the magnitude response and then plot. So, we will be checking the breakpoint again. So, we will set the enable the breakpoint in the next stage and then we will run this. So, I think we will expand this. You will be seeing the combined spectra. Sorry. Almost they are overlapping, you are unable to see even the expansion of it. So, you can reduce the thing. So, approximately it shows at 30 are combined frequency response. So, your resolution what you are going to see is very this thing small in this case. So, we may have to increase number of samples. So, what we can do is I can sample at this thing, what we will call it as 1024, we can modify this, sorry, 1024, and whether number of points, whether I can increase it to 256, we will see the thing and then we will rerun the code again.
She had your dark suit and greasy washwater all year.
Actually, it has gone off to further. Okay, we will clear all the breakpoints and now we will put the breakpoint here and the next breakpoint will be in the next place.
She had your dark suit and greasy washwater all year.
Okay, so 1 second, clear all. Will I will break the thing so that we can restart it because it has gone into the end. So, we will come back and then run that portion. So, I have to put the breakpoint now where we are calculating here Fs we had given it as enable the breakpoint here and then again we will enable the breakpoint here. So, it has come to this. So, you can see that it the previous one what we are seeing it as the output. So, now I have to run it again because it is pointing to here, we will continue the thing. So, now you will be seeing that all the sorry it has been mapped to only 64 points. So, it will be little shifted, you may have to multiply, still you will be seeing that the peak has gone up to 200 and odd. So, whether we can expand it. So, you will be seeing that 60 and 61 almost has got merged in this, that is what we call it as frequency resolution, which we are unable to look into the thing. So, now what is it, how we are going to compare are rectangular and Kaiser windows for spectral analysis. So, the next example. So, here the sampling frequency is 256 and we have n is equal to 128 points, that is what it says, sampling rate and then signal length, and then the frequency selected is 61, that is sine wave what we are going to generate it, and then beta value in this case is selected as 8.96, and then we are going to use, instead of alpha we will be selecting beta in this case, W and Kaiser n comma beta we will be applying it, and then we are going to do the normalized gain against rectangular window, and then rectangular windowed spectrum what we will be calculating absolute of that, and the other one is we will be calculating Kaiser windowed spectrum from that is normal G into absolute of XLK, and then we will try to plot the thing. So, here we will put again the break point, so that will not spill over. Okay. So, we will run and then see what will be the frequency and then magnitude what we will be getting it. So, you can see that what is the first one what we have it here is absolute of xk. So, that means to say which is the window you are going to have it, rectangular window here, and then this is my rectangular window and this is the Kaiser window what it is representing. So, with the beta selection, so we will be having the response of the Kaiser window as this way. So, you will be seeing that the almost equivalent to rectangular window the main lobe what you will be selecting it. So, you will be seeing your frequency will be approximately 61 hertz, both of them are passing with both rectangular and then Kaiser window. So, we will see how to find the power spectral density of two sine waves embedded in our random noise. So, you can generate a random noise, that is initialized random signal generator. So, and then your sampling frequency what you have chosen as 1 kilohertz, and then you will be having generate Fs by 10 is you will be seeing that 100 samples of the every one point what you will be selecting it, and you have been given what is it, amplitude of two sine waves, that is 1 and then 2, which is 150 and 140 frequencies of sine waves, and then amplitude of the first sine wave is 1, second sine wave is 2. So, generate xn with a sin 2 star pi f star t plus 0.1 times the random value what you will be adding with your signal. Then you will be calculating your spectrum and periodogram. Okay. So, that is what the next assignment or lab portion of it will again enable the breakpoints here. So, we will run it and then you will be seeing the spectral density here. So, that is what your power spectral density. So, what we had was two frequencies 150 and then 140. So, you will be seeing that this is approximately 140 and this is approximately 154 or something, approximate what you have the thing, and you will be seeing that how your side lobes are buried in your noise what you are seeing it. Fine. So, the next one is whether we can play and compute a spectrogram of speech file in this case. So, Okay. Next, we'll put the this thing. In this case, you have a speech file sampled at 8 kilohertz. You can record it using MATLAB, and number of bits chosen is 16 bits in this case, and sound AC is play the speech signal, and then you can find its spectrogram using the function spectrogram. Okay. So, we will see that first, and then we will look at
She had
it.
your dark suit in greasy wash water all year.
Hopefully, you have heard the thing. This is the speech spectrogram what you will be seeing it. So, you will be seeing that your power frequency 0 dB per hertz what it is shown. So, these are the 50 hertz, and this is frequency in kilohertz what it is marked. So, most of the speech signal, as we say that it is going to be up to 3.1 kilohertz. So, that is the reason why or maximum 4 kilohertz, that is why the sampling frequency is chosen as 8 kilohertz, and time duration in seconds, this is the 3 second. So, this is how you can generate your sine this thing speech signal and see its spectrogram. So, now what we will do is we will overlap add techniques for fast convolution what we are going to use it. This theory we will be covering it in the how to do this fast convolution will be covered in the theory, and then how to implement FIR filter that attenuate this whatever 1 kilohertz sine wave tonal noise speech file. So, what is it? So, you will be using the same speech file, and then sampling rate is chosen as 8 kilohertz. So, first we will be playing the original speech signal, then pure that is what speech is played. Then what you are going to do is you are going to generate a 1 kilohertz sine wave which is called omega 2 star pi into f by fs frequency of sine wave. So, you have done the thing, and you will be merging with your speech signal, that is what we call it as correct speech by 1 kilohertz sine wave, and then you can hear that correct voice, and then we can display the spectrogram of noisy speech, and then later on we will be applying a window technique, that is passband filter 900 to 1100, fs by 2 is 4000 in this case what we have given, and apply FIR 1 filter with stop band, that design an FIR filter to stop the frequency. This is a band stop filters, what it is not band pass, it is a band stop 900 to 1100. So, we want to eliminate 1000 hertz. So, that is why it is a stop band filter what it is designed, and then you will be passing this coefficient B coefficient through your FFT filter, that is FIR filtering using overlap add method is being used here. So, that it is a continuous signal or input signal what you have it. So, you will not be able to take the complete FFT. So, part by part what it will be done actually in the overlap method, add method is being used. So, we have the overlap save method also, one of them can be used here. Overlap add method is going to be demonstrated. So, you will be displaying the spectrogram of the filter speech, and then you will be hearing your output. So, we will run to the end.
She had your dark suit in greasy wash water all year.
So, that was the original. So, we will give a.
She had your dark suit in greasy wash water all year.
So, you are seeing 1 kilohertz sine wave is overlapped with the speech signal. Clearly, you can see that this is a noisy signal. So, we will go back and then press the this thing.
She had your dark suit in greasy wash water all year.
Although you faintly see the 1 kilohertz, but still in the speech you are unable to hear the sine wave. So, this is a filtered output what you have got it. So, this shows that how our discrete Fourier transform is computed using FFT method to implement for different applications. It can be circular convolution, linear convolution, or you want to eliminate your noise from the speech using the filtering technique. So, we can do it in the frequency domain. Thank you.